Good day, I'm Dr. T and welcome to my office. So today I would like to talk a bit about sound. So sound is going to be a longitudinal wave. It goes back and forth instead of the transverse wave, which is up and down. We're used to seeing the transverse waves, think ocean waves, but of course sound is longitudinal, so it's going back and forth. Now, when thinking about it, the peaks of the transverse wave would correspond to high pressure regions where kind of the air particles have squished in together for a longitudinal wave, and then the troughs would be low pressure area where they spooshed apart. And so you're going to have air that's going to go high pressure, low pressure, high pressure, low pressure, that kind of scenario going through it. Now, like all other waves, it still has its same four key properties. Amplitude, that's going to be volume. The more they squish, the more it's going to push on your eardrum, and the more it's going to start squishing your inner ear, and it's going to be louder to you. The frequency is what we know of as pitch. So the tone of something is going to really just be its frequency. Now you will find that if you give a pure frequency, it's going to just kind of this like beep sound that's really kind of annoying. It doesn't have the warmth or the richness. What we call the timbre, that individual tone color that an instrument or voice has, that is coming from the fact that most things don't just make one frequency of sound. They're emitting quite a few of them, typically in very specific patterns that we call harmonics or overtones. And the blend of intensities of these different higher frequency sounds that are being co-generated give it that individual tone color to it. Now, speed of sound is, of course, important. We can think about, airplanes traveling faster than the speed of sound, etc. However, it has a rather interesting relationship with pitch. Typically, what's determining the frequency created by an instrument or a voice or any other kind of sound generator is quite often not the frequency itself, but the actual wavelength. Because what's usually taking place is something is causing vibrations in the air, and the size of the cavities or the strings or whatever that thing is using to convert this kind of random frequencies into a nice tone is selecting certain wavelengths of sound that can create standing waves that can resonate within the instrument, and then those become amplified with constructive interference, and then other types of wavelengths are diminished with destructive interference. This is why, taking a violin and pinching your finger, let's see if I can get this on camera, pinching your finger closer to the bridge is going to raise the pitch. You're shortening the wavelength, and moving it backwards is going to lower it. Of course, you can see this probably the most clearly in a trombone. Make it bigger, make it shorter. That kind of scenario. Now, if the speed of sound were to change, then all of a sudden, the wavelengths don't match to the same frequencies because it's wavelength times frequency equals speed. And you can change the speed of sound by changing what it's traveling through. You can change the medium. You can, of course, hear this if you dunk your head underwater. The frequencies change quite a bit. Things sound really trippy once you're in the pool, underwater. And even normal microphones and speakers really kind of have to be modified, obviously not to short out, but also, kind of to listen underwater. It's a little bit of a different game down there. But you can also do this by taking the medium and replacing the gas from normal air, which is nitrogen and oxygen, with something that's lighter weight, like helium. And so, of course, you've heard people that have, inhaled some helium from a balloon, and they talk like the chipmunks, a really, really high voice. And that's because the wavelengths that were corresponding to their normal frequencies now correspond to much higher frequencies. You can do the opposite with a heavier gas, something like argon or xenon, where you inhale those and your frequency will be much lower. There is a safety consideration with the heavier gases because, your lungs need air in them for reasons that are not involving sound, living. If you've got helium, it's hard to have an inert gas suffocation because you open your mouth, the helium rises, and air will come in. It's not impossible, though. There are scenarios where you have to be worried about helium safety, although those are rare. With the heavier than air gases, you basically have to stand on your head for the next half an hour or so to make sure you get them all out of your lungs, because they will just sit there and it'll be very hard for you to actually exhale them. So I do not encourage you to try the heavier than air gas inhalation technique at home. Now, one more point I'd like to talk about sound, and that is the Doppler effect. You can, of course, hear this classically if you've got a train. But what's happening is the source of the sound or the listener, or both, are moving. And as the distance is closing, because the two are coming closer together, then the frequency appears higher than what it really is, because you're actually moving into the waves. So as the train comes towards you, it's going to sound higher pitched than it really is. And then as it passes you, you're moving away from it, so the distance each wave has to travel is further, so it's going to take a little bit longer for them to reach than what they would otherwise do so. So it's going to have a slightly lower pitch to the sound, and so you get this classic eeew as the train passes by. We see this with light as well, with what's known as red shift and blue shift, and I will speak more on that when it goes into light. So with that said, have a wonderful day.